Okie dokie, guys. Okay, so a couple hours ago, I just got finished talking to you guys about chapter 14. And right at the beginning of this chapter, we start with dynamic range. Well, I just ended talking about compression, which is dynamic range. So it's a little bit of a repeat here, but dynamic range is measured in decibels. The example they give in the book, I think is pretty good, so I went ahead and used it, is it's kind of a number of choices in a range, number of choices from highest to lowest. And there are choices within that range, which are easily seen. But there are other choices kind of towards the periphery that may or may not be well imaged, recorded. Like, for instance, they said in this scale that kind of more or less starts at 30 pounds. Anything less than 30 pounds, it just says it's 30 pounds because the scale is not very accurate. It's an old analog scale, which until you put a medium-sized dog on it, it doesn't do anything. On the other hand, it can't handle too much weight. And so once you go up to 295, you're fine, 299, you're fine, 300, then you go to 301 or 310 or 400. All of those numbers are going to simply max out at the maximum weight limit of this scale of 300. And so if you have a large dynamic range, well, you might have a scale then that goes from 0.1 pounds to 1,000 pounds. That's a much larger dynamic range. And it gives you more of a subtleness, especially at the far ends of the degrees of different weights. Now in ultrasound, obviously we're not dealing with weight, we're dealing with echo strength. Echoes turn into voltages, turn into pixels. If we have too much of a dynamic range, our eyes can't pick up. We don't notice the difference. It's kind of like noticing the difference between 500 pounds and 501 pounds. If it's sitting on you, you really don't know the difference. Same thing with at the far other end, perhaps you would know the difference between 1 pound and 2 pounds, but 1 pound 1 ounce versus 1 pound, you might not notice. So there are our personal ability, our human ability to see the difference between value points or not. And so if our dynamic range is too wide, we see the ends, but we don't see the individual points. If the dynamic range is too low, then we go from a very bright to a very dark environment or image very quickly, and we end up getting kind of more of a black and white image, and that doesn't help us either. So we do want to be somewhere in the middle of our dynamic range. Let me hold on to you here just for a second, sorry. Well, no, actually I do have it down here. Compression of the dynamic range. Now, you guys saw me with my sponge the other day. That's my dynamic range sponge, and I like to squeeze it. And I like that analogy because the dynamic range sponge, the highest values we can place at this end, and then the lowest values over at this end for a wide dynamic range. We can decrease that dynamic range, and the highest values, circle the arrow, are still at that end, and the lowest values are still at this end. The middle value is still here, but they're all a little bit closer together. In other words, this image would be more black and white. So a wide dynamic range, many shades of gray, perhaps too many. Low contrast, I'm going to pause. I need to read something in the book. Okay, where was I? I got pulled away. My wife needed some help. The grades. Yeah, I don't like all those. Some of the examples are stupid for what that is. But resolution or narrow dynamic range. I'm just going to read off of page 268. Narrow dynamic range, fewer shades of gray, closer to bistable. In other words, black and white. Images that display few shades of gray are high contrast. Well, okay, high contrast doesn't. See, here's the thing. I've been told, it's been suggested to me that high contrast is always good if you want to see a subtle liver lesion. You want high contrast. I just don't agree. You don't want too much choices or too, because it could smooth out the liver too much. But this high contrast with BS. The two pictures on page 268, by the way, those are both of the liver with the kidneys sitting underneath it, and the one on the top is too high, and actually the one on the bottom's, I'm sorry, too narrow a contrast, and the one on the bottom is I think a little bit too wide, because it's at that width, that many echo choices, you're having a hard time seeing the difference. So wide dynamic range means many shades of gray. A grayscale image that is one that contains many shades of gray has the widest dynamic range. Images that display many shades of gray are also low contrast. And I guess just really the question is whether that's good or bad. And like I said, you just want to be in the middle. Why would you want to be at either end? Okay, chapter 17. That was all chapter 16. Woo-hoo! Wouldn't be awesome if they were all like that. And hold on to your hats. This is going to be a little bit of a ride here, because harmonics, it's like they couldn't leave well enough alone. They have harmonic, and then they have to go and find other uses for harmonics and other ways of dealing with harmonics, and that's what's really tough about this chapter, I would say. So the easy explanation, if you really want to go easy on yourself, and if you want to learn the bare minimum of what harmonics is, fundamental frequency goes in, let's say 2 megahertz, and the body, through just interaction of the sound traveling through the body, creates harmonic frequencies. Harmonics are whole numbers. Even harmonics, the even harmonics would be 2 times the original, 4 times the original, 6 times the original, and there actually are odd harmonics too, but they always occur in whole numbers for whatever reason. So this is not the same as saying I have a 2 megahertz transducer that has a broad bandwidth and 2 megahertz goes in, but also 1 megahertz goes in and 4 megahertz goes in, because it has a multiple frequencies in the pulse. That's not what we're talking about here. We're talking about simply a fundamental frequency of 2 going in and a harmonic of 4 coming out. And this happens. By the way, it's always there are several harmonic frequencies that could possibly be used, but realistically, the only one they use is the second harmonic. In other words, 2 times the original frequency. Oh, that's it. I wrote right there. That's the second harmonic, is the only one that is actually used. Because once you go, if you went 4 times the original frequency, then you're using a frequency that is too unrealistically high and it just attenuates too quickly. So harmonics are formed because of nonlinear behavior. He goes a lot into nonlinear behavior without, I don't think, truly explaining that what that means or why that's significant. But linear behavior, let's see, I drew a little picture over here, is like driving in a car with a smooth shifting transmission. You just step, oh, it's like a Tesla. You just step on the accelerator and you accelerate and you go from 0 to 100 in, I don't know how many seconds. You're either going fast or slow. It does not matter. All that matters is that the acceleration was smooth and constant. That's linear behavior. Nonlinear behavior is like driving a stick shift when you're 15 years old and you never even rode a bike. And so you're going, back up and down, and this, you get whiplash in here, and the person driving in the car with you is gripping the seat because they're scared. That's more like a nonlinear behavior, a nonlinear acceleration in this case. I think this is the order of the book. It just kind of jumped into well, no, actually, I jumped slightly out of order. It's page 270. Very simply, fundamental image. The fundamental image, when you do not have the harmonics button turned on, frequency goes in, frequency comes out. The main fundamental frequency. Yes, there are other frequencies, but that's not what we're talking about now. We're simply talking about, let's just concentrate on the fundamental frequency only. The harmonics is the fundamental frequency goes in, and 2 times that frequency comes back out. All right, let's see if we can illustrate what I mean. Oh, sorry, I'm sneezing there for a second. Okay. Tissue harmonics, chapter 17. We know so far that we have a frequency. There's a certain frequency with a certain wavelength, and it creates a nice sine wave, which, okay, realistically, it's not a sine wave because we all know that that's not actually what sound looks like, but that's how we illustrate it. And this is how we draw it. Now, let's think about what these different parts are, and let's think about some of the things we learned already about speed of sound. Up here is a compression. Down here, rarefaction. In other words, here is where, I'll go ahead and just put it here too. That is where everything is pressed together. It's compressed a little bit, right? But then we have these other locations that are a little more rarefied, a little more pulled apart. So in the rarefactions, the molecules are actually pulled apart a little bit. and the compressions are all pushed together. Well, what do we know about the speed of sound? Density has something to do with it. More dense actually slows you down, but that's not the stronger of the two values that we worry about with the speed of sound in tissue. Density is the less effective. The more effective is stiffness. A very stiff material moves sound faster. So this is like getting on a sailboat, starting up a fan on the boat and trying to accelerate yourself. You can't do it, right? That doesn't make any, well, if you think about it, there's an equal and opposite reaction. You're not going to go anywhere. But this kind of does exactly that. Ay, ay. This does exactly that. It's kind of pushing itself. It's creating. It's like how Wile E. Coyote used to do that. He'd get on a skateboard with a little sail on it, and he'd have like a little electric fan or something, and he'd be blowing out and accelerating himself, which is impossible, of course. But Wile E. Coyote was never concerned about physics, right? So anyways, all right, I'm beating around the bush here. Which part of this wave is stiffer? Compression. Oops. The compression, yes, it's more dense, which doesn't increase speed of sound, but it's when you squeeze something together, it actually does become stiffer. The molecules are pushed a little closer together. They're all kind of pushing back against each other. That creates a stiffer. So an increased stiffness. You could also say increased bulk modulus. Just to mess with you guys. Remember, this bulk modulus and stiffness are the same thing. And then over here, we have a decrease in bulk modulus. And so the sound wave produces its own areas of increased velocity and decreased velocity. So let's look at this. I don't know why I did in different colors, but well, the blue shows that the sound wave is traveling into the body. And then over time, the peaks, the compressions, the highest stiffness areas actually travel a little bit faster than the rest of the wave. At the same time, the rarefactions they don't travel backwards. That arrow doesn't mean backwards, but the velocity is slowed down compared to the rest of the wave. And so in the purple part of the cycle here, it's starting to occur. In the green, it's even more. And on the yellow, it's even more. Or at least the distortion is more. The distortion of wave increases the farther we go in. So by the way, that's our first clue. Harmonics doesn't work at very small depths because it just hasn't occurred yet. So over here, no harmonics have occurred. Over here, yes, harmonics. That's our first little lesson about this. This distortion, by the way, sometimes is called a sawtooth distortion. So what does that mean? It doesn't, for whatever reason, honestly, and sometimes it's a little confusing to me, even after I've studied this for so long, as to why this makes even and odd harmonics, not 1/2 a harmonic or 1.5 harmonics, but just, well, there's no one harmonic, but 2 times the original or 3 times the original for odd harmonics. Yeah, I don't know why. I don't know why exactly why it happens in whole numbers, but it does. And so this creates harmonics. If we if this were 4 megahertz, we eventually get, as at a certain depth, we will have 8 megahertz. It probably continues to distort further on we go, but the problem is that when you're doubling your frequency, you're doubling your megahertz. Think about that. That's kind of weird. One frequency in, another frequency is created there, but it's a doubling. Well, that's all well and good. I mean, we could use that doubling of frequency, right? But the problem is attenuation. So if we went, let's see, 2 times 4 is 8, 4 times 4 is 16. We can't really use that. That attenuates so quickly, you'll never see it anyway. So even if it is created, we'll never see it. So that's kind of the basic harmonics in a nutshell. It's just simply a distortion due to its own compression rarefaction, making part of it go faster and part of it go slower until it actually changes the actual frequency, the actual number of cycles that goes by a point in 1 second. Now, the next thing to know about this, here, I'm going to say one thing that's not mentioned in the book. For some reason, they really talk about, well, they talk about some other things, but what's going on here, what's useful about harmonics, like for instance, why didn't we just start with 8? If you want to use 8, just start with 8. Well, there's a couple of reasons. One of them is that 4 megahertz got you down deep in the first place. It got you, let's say 5 centimeters in with not a whole lot of attenuation. If you had started with 8, your attenuation would be twice as bad as with 4. And so 4 gets you down deeper with less attenuation. The other thing to think about is that 8 megahertz, if we're going to use that, well, what produces better images? If we didn't have to worry about attenuation at all, we would always use high frequencies, but we can't, so we don't. So the 8 megahertz is going to produce, just by the fact that it's a higher frequency, better axial resolution, better image quality. But the book doesn't really talk about that too much, so let's concentrate on what the book talks about, because we can only assume that would be on the SPI. All right, so the beam, as it leaves the transducer, is at its strongest. Yeah, I know we've said the beam is most intense at the focal point, and sure, kind of theoretically, yes, that's what it is, but it hasn't gone under a lot of attenuation at the very beginning as it's just going into the skin. So it's very strong at that point. It's not to mention, it's actually disorganized, but that's another story that doesn't really apply right now, but I just wanted to mention that. So with the beam being very strong, And you're going from the transducer into gel, into skin, into a subdural layer of fat, into muscle, into maybe you're actually going through a lot of there are a lot of surfaces there that can cause some distortions. And also not to mention, you know, the attenuation thing that I already mentioned, not to mention it all, I mentioned it. So tissue caused distortion of beam high on the first centimeter. So we get some distortion artifacts in the beginning. It's also disorganized. He doesn't mention that here, but that is part of the issue as well. The beam itself is disorganized. I mean, literally, if you look at the way I've drawn it, it's kind of a mess. And then as it comes down, it cleans up. Well, that's exactly what beams do. Okay. Harmonics don't even start to form until farther down. So what he says in his book is that the harmonic kind of got a free ride past the ugly first centimeter or two. Okay, I'm not disagreeing with that. I would just only add that it also got a free ride because it got down there with a lower frequency. The lower frequency brought it down with little attenuation. Then it starts to develop harmonics. Okay, so harmonics also form so harmonics do not form immediately. It takes a little bit of time. The other thing about harmonics is that they tend to form in strong beams. Well, that has a couple of good advantages. Now, remember intensity, spatial, spatial pulse intensity. Oh my God. Oh my God. Yeah, as soon as I said it, I knew I was wrong. Spatial peak intensity, peak intensity. That makes a little more sense. Spatial pulse didn't make sense in my brain either. Spatial peak intensity, where is that? In the middle of the beam. Ah, okay. So the middle of the beam, we just simply could say we have more strength in the middle of the beam. There's more, let's pretend there's the number of crossing over constructive interference is best in the middle of the beam, and it goes off a little bit on the sides. So middle of the beam is the strongest. Okay, so our harmonics are going to be created preferentially in the middle of the beam. Okay, that's one thing to think about. So let's draw that. Let's see, harmonics can be purple. And what do I want to use? Let's use U. One of these is, that's the one, okay. Ugly purple though. All right. So it doesn't start immediately. So maybe our harmonics start right about there. And at some point they end. So start there. So in other words, if you're using harmonics for something that's 1 centimeter underneath the skin, not going to work. Unless you use a standoff pad. I'll talk to you about that later though. Start, and then harmonics is also only good for a certain degree. Let's put this as an end point here. And perhaps it's just the attenuation of that doubling, that twice the frequency, the attenuation is too great. So there's a region where harmonics is best. What else did I draw on this picture though? I drew, so let's just start here. I also drew grading lobe. This is a multi-element transducer now. Grading lobe. Well, grading lobes, they're real pain in the butt, but they're also weak. They're never as strong as the main beam. And so harmonics are simply not created in the grading lobes. Grading lobes do cause problems. So if you now put yourself in harmonics mode and you're ignoring the fundamental frequency and only looking at the harmonic frequency, and we'll remember two times the frequency operating frequency, you now have higher frequency, a narrower beam. This is basically, essentially, this is your beam length. I'm sorry, width. So the beam is more narrow. You should have better lateral, you know, the lateral thing. You know the thing. You met me. All right, here, let me pause here for a second. Make sure that resolution, by the way, lateral resolution. Pause. Okay, so I just quickly scanned through that part of the chapter up until page 274, and he just really loves that nonlinear thing. And so he says the formation of harmonics versus the strength of the beam is nonlinear as well. And he has a little graph on page 273 where the harmonic image doesn't start immediately, but it's strongest. In fact, here let's draw that as a strength indicator here. Kind of strongest here, and then kind of bleeds off as we go down. And that makes sense. The farther we go down into the body, the more attenuation of the main beam. If it weakens, harmonics very quickly drop off. So you are going to have an area of harmonics near not too close because it hasn't started yet, but still in the near field, harmonics begins and is very strong. Okay, I'm going to shut up before I ramble on. Okay, so now I have to talk about a couple of ways that manufacturers have manipulated this information. And it was actually hard to draw, but I think hopefully I've got something going here. So there's a couple of harmonics. I'm sorry, it's the same harmonics. There's a couple of ways of processing this information. And I think there's more than one way because manufacturers, they invent this and then they put a patent on it. And so if I'm Philips and I put a patent on pulse inversion harmonics, then GE comes up and says, all right, fine, I'm going to create power modulation harmonics. They do the same exact thing. And I honestly think the only reason there's differences there is because of patents, and companies don't want to be left in the dirt, so they figure out new ways of doing the same thing. So with harmonic imaging, originally what would happen is a pulse would go in. Well, geez, that's not the picture I want. If I'm going to talk about what originally happened, that's not the picture I want. Let me just come over here. Let's see. a pulse of a fundamental, whoops, still on that funny, a fundamental frequency would go in, and then what would come out would be a pulse, or an echo, I'm sorry, of twice the frequency. Remember, twice the frequency traveling at the same speed as sound means that we have to have the wavelength. And so now this pulse has got a shorter wavelength. But I should also say that that harmonic frequency would be accompanied by the original frequency as well. So let's see, that looked more like, all right, I need to get rid of that. So both of these would make it back to the machine. The fundamental frequency echoes would be going back, but also the harmonic frequency echoes would be going back. And so if you wanted the machine to look at only the harmonics, it would put an electronic filter on and just filter out that, and then only listen to the harmonics. Now, I'm not an electrical engineer. I have a personality. And so engineers have figured out that there's a more efficient way. This is pulse inversion harmonics. I just want to make it slightly smaller here. Pulse inversion harmonics is a way of filtering out without having to use a filter. For whatever reason, the filter, the electronic filter itself was not perfect. So with pulse inversion, and you're just gonna have to take this for granted. If something doesn't make sense, I mean, go ahead and ask me. I'm not saying don't ask me, but not all of this makes 100% sense to me, because what they show in the book and what I've shown here is two pulses, pulse one, pulse two. One of them is inverted. And you guys know what happens when you have peaks and valleys meeting up with each other, peaks and rarefactions meeting up with each other, it filters out, right? Except it's actually pulse, then another pulse. They're actually not running next to each other like this. They're running one after each other. And so how exactly they're supposed to interfere with each other when they're not running with each other at the same exact time is a little bit beyond me. I think there's a delay inside of the beamformer, as it were. But in any case, these two pulses come down. They hit a surface and they come back. They create, I should draw in a, they also create a higher frequency harmonic. That's going back as well. But let's just look at these purple pulse one and the inverted pulse two. They go in, they strike the transducer, they become basically electric voltages, but I'm showing them as still a wave. Little electric voltages, they come into the beamformer and they cancel out because one of them is inverted. And we know that when a trough and a peak and a trough, when these two line up well, it does this. It goes from two waves that are perfectly out of alignment so that they're destructively interfere, and you have basically nothing. That's a zero, no electron, no voltage. But all this time, this guy, the harmonic frequency, he goes in and he's happy, goes through, and he makes it, let's come up here. He makes it all the way through the system. Did I say beamformer? Or is it, well, probably the receiver this occurs. So once again, 2 pulses sent in, one of them is inverted. They hit something in the body, comes back to the transducer. Each is still inverted. The echoes are still inverted, and those 2 inverted echoes are now combined and canceled. All right, great. So that was the invention of one company. Then another company came in and said, well, I got power modulation harmonic imaging. And they're like, what? Like, that's cheating. I'm like, no, it's not, man. It's totally different. Totally different. It's not totally different. It's actually the same exact thing. They just go about it in a slightly different way. Power modulation harmonics. So on this one, we have 2 pulses that are not inverted. Although I think your book kind of shows an inversion in this, and that's not necessary. They're not inverted. Oh, wait a minute. Our power modulation, I'm distracted. 2 consecutive the second pulse is twice the strength of the first. Its harmonics is weaker reflection does not contain it. During reception, reflections. Well, the book doesn't say anything about them being inverted, but now I'm starting to question that. So let me just tell you what happens. 2 pulses, first pulse, second pulse. You notice that the second pulse is twice as strong as the first. Same frequency, same wavelength, but twice the amplitude. And they go in, and once again, they'll hit something and come back. And they go all the way back into the transducer, which produces different voltages. I'm going to put a V there as well. V. Electron voltages. They just go through. And then the smaller one is gained twice as much as the first one. In other words, it receives twice as much of a bump as the first one. It becomes as strong as the first. Reflection. Let me pause because I'm thinking that has to be inverted. Hold on. You know what? No, it's not inverted, because if it were inverted, they'd be stealing from the other company. I know what it is. Of the 2 pulses, only the stronger pulse creates harmonics. This guy does not create, looks like I just crossed out an M&M. That guy does not create harmonics. And so the computer is able to look at the 2 pulses individually. One pulse is just F naught, it's just the fundamental frequency only. The other pulse is the fundamental frequency plus the harmonic. I'll just put 2 times FO. Now the filter, as it were, is able to easily recognize the fundamental frequencies and subtract them out, leaving only 2 times the fundamental. So the F naught or F0 is completely gone, whereas 2 times F0 it remains. That's what it is. I had forgotten that little detail there. And then we're not done. We are not done. Page 278, contrast agents. Yes, so some of you are familiar with contrast agents. You might have been forced to drink that horrible, at least I hear it's horrible, I've never had to take it, contrast for CT, where you have to drink like a gallon of chalk. That puts a contrast in your GI tract. Sometimes contrast is injected for CT and MR, and that contrast makes your veins and arteries glow. You know, that angiogram I showed you of the circle of Willis, that is a contrast. You can't take that picture without contrast. So in ultrasound, contrast is not chalky. Contrast, well, is not, it's not swallowed, it's only injected. We in America don't use a whole lot of it. Ecotechs use it. It's generally not approved in a whole lot of situations for other applications, whereas in Europe, they're using contrast for everything. So our FDA is really taking its time on this, and I'm not sure why, because I think in Europe they've had a lot of success and not a whole lot of issues. I mean, I guess the thing to think about, let's see, yeah, that whole area is blank. Okay, and the thing to think about is air embolisms. Embolisms, you guys know, are bad. Those are what causes strokes and everything. And if you have an air embolism, that's not very good either. Air can get stuck in a vessel and stop blood flow. It won't be there for long, but it'll be there a little while. Anyway, good way to kill someone. Anyway, contrast agents, also called microbubbles. So contrast and ultrasound are injected. They are microscopic bubbles. These bubbles, well, we'll talk about what they're made of later, but they're filled with air. Sometimes they're filled with medicine, which is kind of cool, which I'll talk about in a sec. They are injected into circulation or ingested. No, I know of no microbubbles that are ingested. Contrast agents have a different acoustic fingerprint than blood or tissue. They are designed to light up blood vessels or other atomic regions. And yes, they do light up quite well. Contrast agents must meet the following: safe, metabolically inert, long-lasting, at least long enough lasting, strong reflector of ultrasound, and small enough to pass through capillaries, which would be rather important. Contrast harmonics. Okay. And once again, he just loves this non-linear behavior. I don't really, this word you use, non-linear behavior, I don't know that it means what you think it means. Just for you, Mac. Okay. So as we know, this is truly what a sound wave more or less looks like. The compressions are dense areas, the rarefactions are pulled apart and they're less dense. So if I have these waves of compressions coming down and hitting a bunch of microbubbles, you can imagine they're going to vibrate. You're bouncing them with pressure, but it's not simply a matter of vibration like a bobber on the water getting moved around by a little wave. That's not what I'm talking about. What I'm actually talking about is this would be an image of one bubble over time. We start, let's see, let me just erase just a little bit more of that. We start with the bubble at its normal size, kind of undisturbed size. Then we rarefy the water, let's say it's just sitting in water. We rarefy the water around it. We pull all the water molecules apart just a little bit. Well, that's kind of like the same as saying reducing the water pressure just a little bit. Just for a little moment in time, the water pressure around the bubble has decreased. Well, what's going to happen to the bubble is that it's going to increase in size. That makes sense, right? I mean, if anyone's ever put a marshmallow into a vacuum chamber, you'll see it get bigger. Well, there's no pressure, there's no air pressure around it pushing that marshmallow back in. So then it comes back down to its regular size. And then during compression, remember, during compression, it actually squeezes down. It goes back to its normal size, and then during the next rarefaction, it gets bigger. Now, if you notice the way I drew this, it gets more big than it gets small, if that makes sense. The difference in size between undisturbed normal size, which is, we'll just say is right there, and getting smaller during a rarefaction, I'm sorry, getting smaller during a compression. Here, let me draw it in. Compression, okay. The size difference between undisturbed, and compression is small. You can't squeeze the bubble that much during compression. But during rarefaction, the bubble can become quite a bit larger than its undisturbed state. So, the book talks a lot about that being a nonlinear behavior. So it's a nonlinear wave being created. A nonlinear echo wave being created, nonlinear echo. And that creates a harmonic frequency. A little bit outside of this chapter, but worthwhile since I drew it. If the sound pressure wave, or sound or pressure, same thing, wave is strong enough, bubbles need not be present from the start. Reducing pressure in rarefaction boils liquid. And when I say boils, you can boil liquid at room temperature if you reduce the pressure. Producing bubbles on the spot and cavitating them almost immediately. Very destructive, and it could actually, over time, destroy props, as in the prop on my little boat here, which, there we go, there's my boat. And the prop creates bubbles. Well, you've all seen that. When boats go through the water, they create an enormous amount of bubbles. Guys, those bubbles aren't being drawn in from the surface and then blown out. That's not how these bubbles are created. These bubbles are created because the velocity of that prop is so fast and the water moving around it is so fast. What happens to fast water? Bernoulli? The pressure goes way down. When the pressure goes down, dissolved gases in the water suddenly become bubbles. And those bubbles, by the way, pop. And it's violent popping. When you look at an old prop, you see it just pitted and damaged. And well, okay, sometimes the damage is because you ran aground, but most of that damage is actually from cavitation. And so I drew a little picture up here. The last bubble popped. The rarefaction is the most dangerous part of this wave, not the compression, because the rarefaction pops these bubbles. And when they pop, it's actually on a very tiny scale, but still significant. It's a violent popping of that bubble. Okay, little fun fact. So what else do I have pre-prepared? Oh my God, I think that might be, yikes. Okay, let me pause and see what I've forgotten. I'm sure there's some. Okay, mechanical index. This is actually a number that next time you're on the ultrasound machine, look for it. There's always an MI somewhere, and mechanical index is peak rarefaction pressure divided by the square root of frequency. Now, we're never going to work on this, but mechanical index is kind of it's an index that tells us how much strength, or no, I shouldn't say strength, how much work is being done on molecules and the cells and the 6-month fetus and all the embryo, I should say. And so it's a strong indicator of bioeffects. So unfortunately, we have a very strong mechanical index. We'll have awesome harmonics, but can't go too strong because you'll blow the kid up. So with low mechanical index, well, and I should also say, lower frequency and stronger sound waves, in other words, higher power, creates the best harmonics. So back to mechanical index, is it less than 0.1? No harmonics are, all right, I'm all over the place, I'm sorry. It just so happens that microbubbles and red blood cells, the most effective microbubbles happen to be the size of red blood cells. Why is that significant? Because red blood cells are designed to make it through the capillaries. If these guys were bigger, if microbubbles were this big, why'd you hit my eye? Anyway, if they were that big, they wouldn't make it through capillaries and they would cause a stroke. You know, you don't want to be causing strokes. So microbubbles have to be small. But it just so happens that the best microbubbles are the size of red blood cells. So it all works out. So mechanical index, the peak rarefaction pressure divided by the square root of frequency. When it's low, no harmonics are created. You just get regular backscatter, and they call it a linear behavior because with a low mechanical index, these circles. Let's just use this circle guy here. The bubbles kind of go from that size to that size to that size to that size to that size, you know. So in other words, what I'm trying to show, other than some kind of inchworm, is that if there's not enough of a compression and rarefaction on the bubble, working on the bubble, we're just simply going to have regular echoes coming off. Maybe even Rayleigh scattering, since they're the size of a red blood cell. So if it's Rayleigh scattering, arrows going off in all directions. So that doesn't help us much. Higher mechanical index between 0.1 to 1.0, you get some harmonics. You get a resonance. Resonance, what does that mean? Well, that just simply means, here we'll draw more circles because they're fun. Goes from, I'll skip the intermediate size, goes from there to there, to there, to there, and so on and so forth. The bubble gets smaller, gets bigger, gets smaller, gets bigger every time this cycle goes by. Think about how fast that's happening. We're in megahertz, right? Millions of times a second. Boom! Although we're in megahertz, but we're also using pulsed ultrasound, so it's just a quick pulse of a million. Still pretty fast. So resonance just means simply that the bubble is going up, back and forth indefinitely. Some non-linear behavior. Okay, well, that means what it meant before. It gets bigger, then it gets smaller, like a TARDIS. Higher beam strength is required, of course. Oh no, higher beam strength meaning that you're getting more of them. No. Higher beam strength is required to do that. And bubble expands moderately. Strong, highest MI is greater than 1. You get very strong harmonics. You get bubble disruption. So remember the bubble disruption. It pops. Apparently I can't write with circles. Extreme non-linear behavior, which is kind of basically the same as saying really good harmonics. The lowest frequency of sound creates the highest mechanical indexes and the highest beam strength. So you have a low frequency sound plus a strong beam, you are more likely to create harmonics. You're also more likely to pop your bubbles. The bubble expands greatly. Now, something the book doesn't mention, and I don't know why, because contrast works even without harmonics. Now, why was that? Why would that be? Why would contrast work? Let's see, we're surrounded with water, right? And what's inside of here? Some kind of gas. You think Z1 equals Z2? No. What do we see when we look at lungs? Not that you've been looking at lungs, I know, but you should know from at least learning about it. You don't see anything. Everything reflects off of a gas because the impedance difference is huge. So that's the other thing, is that even if you weren't creating harmonics, microbubbles still work. But I guess that's not part of the chapter, so that's why we don't talk about it. Let me talk about the shell here. And let me just quickly read the last 2 pages of this chapter. Okay, well, I didn't really need to draw this. Probably would have been much faster to simply pick up a picture off the internet. And but there's a couple of ways of creating these microbubbles. Well, and the most primitive way is just taking saline and shaking the living daylights out of it. Or forcing air into it and shaking it or whatever. But the problem is those air bubbles, as tiny as they may be, they're not going to last 10 seconds in the body. You know, maybe just a little bit longer. So you would need to inject like centimeters from where you're looking. So simple saline solution, shaken, not stirred, is not going to help us. So there's a couple of different things that you could make this out of. You could make micro bubbles out of certain non-toxic plastics, as long as they're not rigid. If they're rigid and they break like glass, that's not going to help. But they need to be able to expand and contract, expand and contract. And they need to be able to go through capillaries. So they need to be small and somewhat flexible in order to make it through. So one of the things they make them out of is a phospholipid bilayer. This is what this is what your body's cells are made out of. Is a phospholipid bilayer. And if they're really small, which they will be, they're going to be quite small. They're going to be smaller than a cell. They essentially, inside of cells, let's see, I have a human cell here with a phospholipid, edge along around the edge, but there, and then you have little communication cells, well, little bubbles inside of the cell. They could be coming towards the wall. They could be coming from the wall in, depending on whether or not they're expelling their contents to the outside or perhaps bringing contents from the outside in. Those are called lysosomes. I don't know if you guys learned that, but lysosomes are tiny little phospholipid bilayer bubbles. And inside the cell, there's going to be all sorts of, DNA or whatever, or coronavirus, whatever they find. But inside of a purposely built one, there's going to be certain types of air or gas. Now, they can create certain inert gases, not create gases, but use certain inert gases that are bigger than others. If you use helium, well, you might talk funny for a little while, but the thing about helium is it's a tiny gas molecule. It can get out easily. So you want to use larger gas molecules if possible. The other thing is, I'm going a little bit beyond once again, but this is fun. This is good stuff to know. Let's say you have cancer, and the doctor wants to give you a medicine that is very potent, and he only wants that medicine to be delivered to the tumor itself and nowhere else. Well, if you could visualize that tumor and you put an ultrasound beam going through, no, it doesn't, how about this? I'll put the ultrasound beam over here. So that's the beam going in that direction. And that beam is centered on a tumor. And of course, there's blood vessels going through the tumor. What you could do is have a very high, high mechanical index, well above 1 for the mechanical index. And as this microbubble goes through, it pops, because that's what happens with high mechanical indices. They pop during rarefactions because they get so big they can't handle it anymore. And so what if you had a medicine inside of there? So that's kind of an interesting use of a microbubble, is to have it go ahead, let it circulate throughout the body, but explode specifically where you want it to explode, so that therefore that medicine is delivered to exactly where you want it to be. All right, summary of contrast harmonics created during reflection. Okay, created during reflection. Well, that just means contrast harmonics they're not like tissue harmonics, which are created as it travels. Contrast harmonics are created at the bubble. The reflection of the bubble is nonlinear. It creates a harmonic frequency. Created by nonlinear behavior of the microbubble, resonance creates some harmonics, bubble disruption creates very strong harmonics, but it also disrupts the bubble, so that may or may not be okay. Related to the mechanical index, low mechanical index, no harmonics, intermediate, some, high is high. And affected by microbubbles, shell, and the gas within it. Yeah, no kidding. That's kind of the whole point. Table 17.3, tissue harmonics created during transmission, occurs as sound propagates in tissue, results from nonlinear behavior of the transmitted sound beam, some of the beam traveling faster than other parts of the beam, and creates a harmonic signal, but not terribly strong. Contrast harmonics create very strong harmonic signals created during reflection off of the microbubble. So it's not traveling, it's just, yeah, right there. I already mentioned that. Occurs when you have to have the agent present and with MIs greater than 0.1. Results from nonlinear behavior of microbubble. Okay. Chapter 17. That's not gonna lie, that's some heavy stuff there, but I think we did all right. Let me just back up here and look at what we've gone through. Well, chapter 16 and 17. Okay. Read the book, guys. Have the book open when you go through this. It's a little late to tell you that now, but got to read that book because if you're depending on me to explain everything to you and you're not reading along and you're not really trying to fully understand it on your own time as well, you ain't going to get it. People tell me I explain things really well, and maybe I do. But if that's all you're listening to and you're not truly studying the book and getting every question in the chapter and in the back of the book, you're not going to get it. It's going to be hard. So, all right. Well, this should be Monday. At least this will be released on Monday, and hopefully you got something out of it. All right, guys. Adios.